Now, as you know, all physical circuits, they respond after some delay. So if you have a circuit like this, consider this. So here, let us say this is A, B, and C. And so let's have A, and let's assume that it is 1 in this timing diagram. And B starts at 0, and somewhere here it goes to 1. So how will C look like? Well, in the beginning it would be 0. Now that is an AND gate. So since A is 1, when B goes to 1, C will also go to 1. But not immediately, after some propagation delay. So here, you have some propagation delay. Now if you, maybe this is the normal propagation delay, and if you have a delay fault, it could be like this. So in presence of a delay fault, let me show here. Maybe it responds like this. So this is when you have a delay fault. And let's assume this is normal delay. So it responds, but takes longer. And so how can you detect delay faults? And let me give you delay faults. A lot of work has been done on delay faults. And we actually did some of the very early work on delay faults. We established some theorems. We pointed out that delay faults, they have coming up with tests for delay faults is actually sort of related with finding tests for related stuck-at faults. And we did some early work. But right now, we want to see this only briefly. So let's look at an illustration of a delay fault. Now you can model a delay fault in a couple of different ways. Okay, so some of you are ECE. So notice that each node can hold some charge. And the time it takes for it to respond would depend on, among other things, how long it will take for the charge to, how long it will take for this node to charge, or how long it will take for this node to discharge. So that means how is the connection to the high voltage, or how is the connection to the low voltage. And people have come up with different types of models, but one simple model can be that you can have excessive gate delay. Now sometimes people will consider not individual gates but all possible paths, which is a different type of model. But let's assume that in individual gates you can have more delay. Now actually it is possible to have a rising edge affected by the delay, by a delay fault, and falling edge may not be affected by a delay fault. And the reason is that the path to high and the path to low are different. But anyway, let's assume a simple model. So let's consider this situation. Let us assume that here we have a combinational circuit, a simple combinational circuit. And normal propagation delay for all the gates, I'm assuming, is 0.2 nanoseconds. And keep in mind that a nanosecond is 10 raised to minus 1, sorry, 10 raised to minus 9 seconds. Now if you have a let us say if you have a just to make the calculation simple, 1 gigahertz processor is now too slow. Any of you have a PC with 1 gigahertz clock frequency? Okay, how many of you have a PC with 4 gigahertz? Okay, how about 3? Okay, so that is sort of the current technology, 3 gigahertz. Let's assume if you have a 1 gigahertz machine, that means the clock period for that is 1 divided by 10 raised to 9, and that is 1 nanosecond. So between two successive clock periods, the delay is 1 nanosecond. If it is a 1 gigahertz machine. Okay, so so let's assume that here we have a combinational circuit, and all the delays are 0.2 nanoseconds normally. And let's assume that in case of a fault, this delay increases to 0.8 nanoseconds if this has a delay fault. Now, how we will test for this? Now, notice that inputs to combinational circuits come from some storage elements. So let's assume this is a set of storage elements, or perhaps a register triggered by the rising edge of the clock. And maybe there's some internal delay between here and let's assume this is 0.2 nanoseconds. And let's assume that the situation is like this, that at the beginning this was 0, 1, 1, and we are applying two patterns, one after the other. And in the second pattern, we have a transition from 0 to 1 on this one. This stays at 0, this stays at 1, this stays at 1, but this changes from 0 to 1. So what will happen in that case? Notice that since this is 0, so this is going to stay 0, right? And okay, since this is a 1, when this switches, so this is basically a rising edge here, right? Goes from 0 to 1. So since this is 1, you will have a rising edge here. This will go from 0 to 1, right? And this here will go, this is 0, this will go from 0 to 1. So basically you have a transition traveling along this path, right? Now let me have a time diagram here. So let me have the clock here. And let us assume that this is a clock with 1.0 nanoseconds clock period. Between rising edge to rising edge is 1.0. There's a period there. Sorry about that. And now if in the normal case, now what is the total delay in the normal case? Starting from the transition here, 0.2 nanoseconds here, 0.2 nanoseconds here, 0.2 nanoseconds here, so that's 0.6 nanoseconds, right? Now notice here that transitions here, they will flow in parallel. So we just have to consider the longest path. So this transition goes along this path, and in a normal situation, things are going to be stable. Let's say this is about 0.5. So things are going to be stable maybe here. So here we have, this is 0.6 nanoseconds. And so things will be stable here. And after that, this time period is basically the slack. That means it provides a margin. So things are going to stabilize right here. So if you have a rising edge, you are going to see that signal here is going to go up here and will become stable here. But if it is faulty, the delay is going to be 0.2 plus 0.2, that's 0.4, plus 0.8, that is 1.2 nanoseconds. So basically what will happen is that here 1.2 nanoseconds, so here it stabilizes. So your transition is not going to arrive at this point. So what will happen is that on the rising of the clock, wrong value is going to be latched. So this transition does not arrive at right time. So it is going to latch the incorrect value. Here also you have a clock. So, so in this case you can see that this delay fault is going to cause a incorrect value to be latched in the destination latches. And that incidentally gives you a test for the delay fault. Now whenever any chips are manufactured, they are always tested for delay faults. And as I was saying, that delays cannot be exactly controlled. They need to be tested for delay faults. So what they will find is that some chips, they satisfy the frequency requirements. So let's say they are trying to come up with 3 gigahertz chips. So some of them will pass at 3 gigahertz. They will do some testing. And testing basically will require them to have a number of transitions that will travel through the circuit. And they want to make sure that those transitions are captured correctly. And if not, maybe they don't work at 3 gigahertz, but maybe the chip will work at 2.5 gigahertz, lower frequency. So what do you think they will do with the slower chips? Do you think they will throw them away? No, they will actually sell them for cheaper. They still work, except that they're slower. So sometimes the chips are sorted, and the higher frequency chips are sold for a little bit more money, and the lower frequency chips, they would be sold for a little less. Because some people don't care about speed that much, right? Some people do. So depending on what kind of price they want to pay. Any questions or comments? Okay, so this is about delay faults. And now let me talk about transistor level faults. Now I have been telling you that okay, we still have a couple of minutes, right?
Yes, sir.
Okay, so now I want to convince you about the stuck at 0 and 1 fault model. I want to tell you why it is good. There have been quite a few papers on that subject. So if you will find in testing literature, a lot of discussion. And we were some of the early people who, we actually did a lot of experiments. So we had some students, and so he did a lot of modeling using SPICE. So I guess electrical engineers, you have all used SPICE, right? What is the full form for that? The tool for modeling at the component level, resistors, capacitors, and so on. And we injected defects at different levels, and we examined what happens. And so I'm going to show you some transistor level circuits